So my name's Tom Goggle. I'm a market segment manager with BASF Construction Systems. We're based out of Shakopee, Minnesota, but fortunately I just live in Bel Air, Maryland, just north of Baltimore. So it's a pleasure to be here today. They always ask us to give a brief commercial about BASF, so I'm going to do that, and then we'll dig right into our learning materials. In advance, I apologize for speaking very quickly. There is a lot of material to cover, and I'd like to allow some additional time at the end to allow for questions. So BASF is the world's leading chemical company. We're up there with Dow and DuPont, just to name two of our competitors. We serve all major industries. We operate 380 plants globally in 170 countries with 6 Verbund sites. Verbund sites are really cool. What we do is we take the waste product of one chemical process and use that waste in another chemical process. The waste from that becomes used in another process so that at the end of the day, we almost have zero emissions and waste products. So we're constantly looking to be a sustainable manufacturer because we're so large. $85 billion in global revenues. And last year, we filed 800 patents with the U.S. Patent Office. So we're a real innovator. We used to say that at BASF, you don't know the products we make, you know the products we make better. And here's just a list of some of the products that I was asked about. Our audio tapes, there's an image of that. If you're old enough, you might remember those. That for the younger group, this is called a cassette tape. But you can see we're in all segments of industry. When it comes to the construction products that we manufacture, over the last 150 years or so, we've acquired some iconic brands, just some tremendous building materials that are used every day globally. And you can see some of those names that or brands that we've had in the past. But more recently, because we live in a global economy, we brought all of these brands together as one brand, Master Builder Solutions. So the Sonneborn of yesterday is now Master Seal. Thorough Seal is a Master Seal product. So we just renamed, the chemistry remains the same, but we changed the name. So if you're specifying here in Silver Spring, Maryland, but you have a project in Dubai, guess what? The product that you're specifying here is available under the same name across the world, okay? If there's no questions, I'm going to proceed. This is going to be an AIA program, so I'll be manufacturer neutral, or try to be as best as I can. If you feel that I'm straying away from that, please raise your hand and let me know, but I'm usually pretty good about that. So what we're trying to accomplish today is understand how material science, because that's what we are at BASF, how material science bears on fluid applied barrier systems. We want to learn or identify and distinguish between different types of barrier systems for buildings, understand important codes that apply to air, water-resistive barriers, vapor barriers, because there are some code requirements, as well as the fire code. You may hear about NFPA 285. I got a change in the last minute. They're redesigning a building because they found out that their building wasn't meeting the requirements of NFPA 285. So we'll talk a little bit about that. And then describe the 5 essential requirements for air and water-resistive barriers. So material science, barrier systems, system requirements, and code requirements. All really important. We're going to cover that today. So why are you here? Well, hopefully to enjoy a great tasting lunch from Panera Bread, but also to recognize that there's some distinct advantages that barriers bring to your owners and to your buildings. First of all, the return on investment for an air barrier is out of this world. If you think about the fact that air barriers can impart energy savings or a reduced energy load for a building up to 36%. That's remarkable considering the small investment up front required by an owner. Of course, the owner doesn't have a choice anymore because more recently, air barriers have become part of the energy code, and the energy code has been adopted in Virginia and Maryland and many other states. So now it's a compulsory requirement as well. Another reason that barriers are important is because of litigation. If there's one thing that destroys a client relationship, it's a lawsuit, right? I mean, everything starts being flung, and the reality is that barriers are a huge part. The building envelope and failures to the building envelope contribute a tremendous amount towards overall construction litigation. So anything that we can do to get a better understanding of the building envelope and the components of that envelope to prevent litigation, that's time well spent. Last but not least, the designer's archetypal dilemma has been water and the effect of water on our construction. And the building envelope is the first defense or part of the defense against that intrusion of water. Just think about it. I travel a fair amount, and I stay in Hampton Inns usually, and that's a 6,000 square foot. Okay, if you take 1 inch of rain on that roof is going to collect water. All right. St. Louis, as an example, we took a midpoint in the U.S. has about 44 inches of rain. So when you do the math, that roof has to manage 164,000 gallons of water. Now, as a point of reference, a bathtub, okay, a residential bathtub is about 40 gallons, all right? So that's a lot of water that building has to manage over the course of a year. And just hypothetically, let's suppose that 1% of that 164,000 gallons of water enters the building envelope, all right? That's 1,600 gallons of water. That's, well, do the math. It's a lot of bathtubs of water, right? That can cause problems, and often it does. So it's an important topic, and hopefully we'll add some clarity and better understanding through this program. But at the end of the day, construction defects create added cost and burden to all project participants. So, what about material science? I used the term earlier. What does it mean? Why is it important? Well, building science is an interdisciplinary field that is really charged with and involved with the discovery of new materials with a particular emphasis and concentration on the creation of new solids, bringing one material together with another, blending them together to create a new material. And hopefully that new material has maybe lower cost, higher performance, and we make the world a better place. If you think about it, when it comes to barrier systems, I showed 3 here. Even as different as they are, we have a mechanically fashioned sheet right here. We have an SA type peel and stick here. Here's a fluid applied. As different as these materials are, guess what? They all contain solids. Now that might be intuitively unclear, because if you think about a fluid applied material, you think it's you know, a liquid type material. But consider the fact that every gallon of paint that you get, or every coating that you have, has both a solids content and a solvent content. Now here I use the term solvent as we use it in chemistry. It may be water, it may be a hydrocarbon-based solvent, but the point is that the solids are in an aqueous solution, okay? And that solvent is there for really only one purpose, and that is to get the solids to the target substrate, to what we're trying to protect, because it's the solids that last. It's the solids that provide protection of our target substrate. The solvent, whatever it is, if it's water, it'll evaporate. If it's a hydrocarbon, if it's mineral spirits, it'll flash off, right? It goes away, the solids remain. So looking at the solids is important to understand performance. When it comes to air barriers, the mother's milk of an air barrier is its air permeance. Now, every time I say air permeance, I usually get, I create a little bit of confusion, because when we think of permeance in architecture, most often we're thinking of vapor permeance, right? And there's a difference between air permeance and vapor permeance. Air permeance is measured by ASTM 178. And conversely, vapor permeance, we use an entirely different ASTM E96. when we look at these 5 different barrier systems, this is information as reported by ABAA, the Air Barrier Association of America, so it's a neutral organization. It shows that there's a wide variance in the air permeance. Now, air permeance in an air barrier is bad, okay? Because it means that more air is passing through the air barrier material. So if an air barrier is to stop air, well, then it would stand to reason that a lower air permeance might be a better performance characteristic. And so you can see these different materials here. Now, that being said, each one of these 5 materials shown here meet the energy code. But as a basic building block to an air barrier, as a designer, you may want to select a material that has the lowest or a very low air permeance because it goes a long way to the overall performance of your air barrier system. Now, what I've overlaid on this chart is the wet mill thickness, because these are 5 fluidified air barriers that we're looking at. And you can see that the film thickness as shown on the axis on the right is all over the place, and that the air permeance is also all over the place, but that it does not line up in terms of the thicker, the better the performance. In fact, the highest performing air barrier from an air permeance standpoint, all right, has the lowest, can be applied at the lowest thickness. Why do I point this out? Because it's material science. You see, if you use a different science, a different material, all right, you may have to put a lot more material on to get the same or hopefully better performance, but we see that that's not necessarily the case. Material science is the backbone to air barriers, regardless of what type of air barrier they are, fluid applied, or sheet membranes, essays, etc. Consider this. Let's talk about vapor permeance now, or vapor barriers, all right? The quintessential vapor barrier is this material right here, right? 6 mil poly, right? That's what we used to use in architecture as a vapor barrier. But the reality is that it's really not a vapor barrier. It's a vapor retarder. And the building code now classifies vapor barriers as vapor retarders. In other words, it's done away with the terminology of vapor barrier because it's misleading to the designer and anybody else that is touching the material or installing it. Class 1 vapor retarders are the old vapor barrier. They have a very low vapor transmission characteristic. And I show it here, 6 mil poly, over here as a class 1 vapor retarder, okay? Now let's compare that material, a very thin material, okay, to something a little bit heavier or thicker, all right? Gypsum, latex prime gypsum board, okay? What we see is that the vapor barrier, the 6 mil poly, has a very tight membrane. It doesn't allow vapor transmission to occur, all right? If I make it thicker, let me ask you what happens. This is a question. If I make the poly thicker, does it go in this direction, or does it become more vapor permeable like that thick drywall material? Anyone want to take a stab at that? Well, the reality is it actually goes in this direction. You see, it's a different material. Clearly, this material is different from this material. It has different performance properties. This thicker, it doesn't become like that material. It doesn't perform like that. It goes in the other direction. So having an understanding that different materials have different properties is important, lest we get confused and make an error. Now check out the green bar. This represents on the graphic here 2 mil polyamide film. All right. The key here is 2 mil polyamide film. Notice that its vapor permeance range goes from a class 2 vapor retarder all the way to a vapor permeable material. All right. Let me ask you this. What's happening to its thickness across this vapor permeance range? It's 2 mil polyamide film. The point is nothing. It's 2 mil polyamide film, and yet it has a wide vapor permeance range. What is going on here? Right? The point is that thickness is not a measure of performance, but a measure of dimension. And using a thick material may lead you down to thinking that you have a higher performance when you may get totally screwed up and not have what you want. So here's the reality with polyethylene, right? As the polyethylene gets thicker, as noted with the blue bars, its vapor permeance actually decreases. It becomes even tighter and tighter of film, yet never reaching quite zero. Everybody's interested in VOCs because it talks about sustainability and green building. Here are those 4 of the air barriers that we looked at earlier, along with their VOCs. You can see that as you get thicker, the VOCs actually decrease, right? These 4 materials all share a common chemistry, broadly speaking, but if you change the chemistry, you can see that the contrast here, where you're actually applying less and still have lower VOCs. So material science matters. Thickness is not indicative of performance. It's indicative of dimension. Let's move on. So there's a number of different types of materials that are used in barriers. We have mechanically fastened sheet. We have the self-adhered membranes. We have the fluid applied, and we also have now board stock. A number of manufacturers have impregnated their board stock with certain water-resistant materials to help them act as a dual functionality. One of the concerns that you may want to have is that when you try to combine functionality, okay, you may get tripped up. As an example, there's a number of air barrier manufacturers that state that they are an air moisture barrier, all right? But does that mean that they're also a water-resistive barrier? And does it matter? What's the difference? We'll explore that a little bit further. We're also seeing, more use of vapor permeable. The first air barriers came out of Canada, okay? What do we know about Canada? It's freaking cold, isn't it? It's really cold. So up there in that climate zone, we're inclined to use a vapor barrier, all right, or an air barrier with a very low vapor transmission characteristic because of the dynamics of that climate. But 20 years after the birth of air barriers have migrated into warmer climates or mixed climates. So at what point, where in the wall do you want to have a vapor barrier? And do you want to have 2 vapor barriers? That's never a good idea, right? Right? Double vapor barrier, vapor's going to get trapped in there. So we see in mixed climate zones more use of these vapor permeable, especially with stud cavity construction. The first challenge in construction and building design is water, as we mentioned before. Managing vapor and bulk water is really important. And the fact of the matter is that if we install an air barrier, we do a lot to keep our walls dry, right? Because, we have a storm brewing outside right now as we speak. What's bringing that moisture? It's going to dump rain. I saw there's flash flood warnings in some parts, or, storm surge, whatever they call that for small boaters. What's bringing that moisture to us? Air. Right? The wind is bringing that moisture to us. And the same applies to our construction. A small hole in our wall assembly will allow air leakage, and with that comes moisture. Then the problem, once that moisture is inside our wall system, what happens about dew point, right? And interstitial condensation. Because that vapor that's coming to us, when it reaches its dew point, becomes aqueous. It becomes a liquid. And that's when it becomes a problem, because that's what wets out our building materials. That's what's going to, look, metal studs rust, wood studs rot, gypsum crumbles when it's wet. See, we still are forced to use a lot of materials in our design and construction that don't act very well when they get wetted out. This is particularly problematic if the wetting rate exceeds the drying rate of these materials. That's where a vapor permeable air barrier may make sense in mixed climates. So 90% of the moisture intrusion occurs within 1% of the building envelope. That's not my quote. That's out of a construction textbook. And when I first saw this presentation, I said, well, we really should, you know, indicate who said that. And so one of our tech guys actually did some digging and found the source of that. And it's some important guy that wrote a textbook, if you're wondering. And I don't remember his name, and we have to put that there. Just in full disclosure, I wanted to point that out. But if you think back to that original analogy that we had about that Hampton Inn roof, right? We said 1 inch of rain, 1% of a year's worth of moisture getting into our assemblies, it could amount to 1,600 gallons of water. Folks, that's a lot of water, all right? That creates problems for everybody. So the 4 types of barriers, right, are air barriers, water-resistive barriers, vapor barriers, and then these multifunctional barriers, okay, which might include thermal barriers, all right? So that's what creates our building envelope. But the fact of the matter is that an air barrier is not the same as a water-resistive barrier. And a water-resistive barrier is not the same as an air barrier, and we're going to describe the differences. But when it comes to air barriers, we want the air barrier on all 6 sides of the building. And that's the first difference between an air barrier and a water-resistive barrier. You see, a water-resistive barrier is mandated by code on the exterior face of the sheathing, okay? A designer doesn't have a choice of where and when to use a water-resistive barrier. He does have a choice where and when to use an air barrier. The air barrier is all 6 sides, but where in your vertical walls that air barrier shall lie is your choice. It is not mandated, okay, in the energy code. It is not mandated by any principles of good design. But what we do typically see is that that air barrier is being installed on the exterior face of the sheathing. That's where a water-resistive barrier is supposed to go. And we know that because it's in the building code as well as required by the manufacturers of sheathing products. Air barriers all 6 sides. Water-resistive barriers are designed to keep water out. Air barriers are designed to keep air out. And if you think about it, and I see this time and time again, the details for an air barrier are different than the details for water-resistive barriers. If you think about your building or shingling a roof, where do we start at the bottom, work our way up. So every successive layer of material is draped over top or shingled over top of the preceding. With air barriers, this is not the case. We want the air barrier to be continuous behind any of these flashing materials. So to to install our flashing sequence of construction, to install our flashing at base of wall and bring our air barrier to tie into the top of that, okay, what's going to happen? Air is going to leak below, underneath that flashing, behind that 6 or 8 inches that is unprotected and leak into the building. Guess what? Plate lines are a huge leak point for a building with air, okay? Water-resistive barriers are different from air barriers, not just in that they're designed to handle different environmental loads, but also in the way we detail for them. So use caution. And this is why I said these multifunctional barriers, we really have to pay attention because the function of an air barrier is different than the function of a water-resistive barrier. We could get all screwed up. Vapor barriers, well, as the name implies, vapor barriers are intended to stop vapor, or as more appropriately stated, to retard vapor, okay? Their position in the wall actually does matter, all right, unlike the air barrier. So if we're now using an air barrier that is also a vapor barrier, such as the first air barriers that were created, everybody used to say, oh, you know, where's the AVB, right? Has everybody heard that term, AVB, air vapor barrier? But guess what? We're not using AVBs anymore, oftentimes. So let's not call them that, lest, like I saw on a project in Guantanamo, they brought in an AVB when another material was actually required. Materials can provide air barrier function, vapor barrier function, and water-resistant barrier function. But the question is do they? They can, but do they? And the designer really has to pay attention, and it's really the architect's responsibility. What I see is that oftentimes the architectural firm subcontracts or enters into an arrangement with an envelope consultant. And it makes sense, right? Because earlier in that one of those first slides, we saw that litigation is so prevalent, right? And so let's transfer the risk to an engineering firm to evaluate this stuff. The problem is that if you read the engineering firm's contract, you see that his finger's pointing to you like we're not taking, we'll take your money, but we're not going to take any responsibility, right? So it's a fine line. But at the end of the day, the engineering firm rarely is engaged for a code review. You guys as architects need to know the codes, and they're different for air and water resistive barriers, and we'll talk about that. So this is an ugly picture. I took this outside of Boston about 3 years ago. And you guys make out what this is? Wood framed wall, OSB, or what used to be OSB, 2x4 studs. What's in the back on the interior of the wall? Can you make it out? What is that? Yeah, well, it's polyethylene. What is it doing there? Well, as intelligent designers, we can say, well, it is serving one of two or maybe two purposes. It is either an interior side vapor barrier, which is appropriate for that climate zone 5, or it's acting as an air barrier because it has an air permeance of less than 0.004 CFM and a pressure differential of 75 Pascal. And as we discussed earlier, air barriers can be placed anywhere in the wall design, even on the interior. In fact, I hate it when that's not drywall, but drywall has an air permeance of less than 0.004 CFM and a pressure differential of 75 Pascal. And drywall is an air barrier material. All right. So extending this, the problem here was not with the vapor barrier. The problem wasn't with the air barrier. The problem was the sheathing rotted out. And what goes over sheathing? As I mentioned before, a water-resistive barrier. The problem was the water-resistive barrier. This is what happens when water gets into our building envelope. All right, it creates a lot bigger issues than if a little bit of air or moisture vapor comes into our wall assembly. Bulk water management is critically important. And here's where we see another distinction with distinction between air barriers and water-resistive barriers. We mentioned about the details, but let me ask you, all right, what do we flash for, air or water? Water, right? Yeah. Yeah, it is a water management device. In fact, in design and in the code says that the water-resistive barrier shall be tied and connected to flashing to divert water to the exterior of the building envelope. Flashing is a water management device. Lo and behold, what we started to do is we started to connect our air barriers to flashings. A great termination point on turn-ins to our buildings, like our window openings, right, that are required to be flashed. So we tied our air barriers to these flashings, and I guess we figured like that makes the air barrier a water-resistive barrier. Not true. Not true. The definition of a water-resistive barrier by code is actually kind of complex, and we'll look through that. Air barriers are so different than water-resistive barriers that guess what? They're in different codes. Air barriers are discussed in the energy code. Water-resistive barriers and vapor barriers are discussed and addressed in the building code. So Friday is 2 days from now. You guys get paid Friday? Or is it next Friday?
I think we got paid last Friday.
So you're every 2 weeks?
Yeah.
Okay, so when you get paid next Friday, are you going to pay federal or state taxes?
Both.
Both? Well, so what should we follow, the building code or the energy code? Both. Following the energy code for an air barrier, when we have a different code for a water-resistant barrier in the building code, we don't get to pick and choose, right? We got to pay our taxes, both taxes. And likewise, we have to follow both codes, and there's differences. We'll talk about that. So the 5 basic requirements of a barrier system, all right, and specifically an air barrier system, are first, continuity. And guess what? This is actually a mandate in the energy code, that air barrier material be installed continuously. It doesn't tell us where. It just says continuously within the thermal envelope, all right? But it doesn't, but what it imparts and emphasizes is that a barrier, no matter what type of barrier, vapor, water resistive, or air, It doesn't work if it's not continuous. And this is another thing that I see a lot of manufacturers say, that, well, this is our air barrier system. This is we sell an air barrier system. It's an air barrier system. Well, guess what? No, it's not. No manufacturer in the world manufactures an air barrier system, right? Because when I give you an air barrier, something like this, I'm giving you a material. How is this created to be continuous on the wall? It has to be installed, and it has to be compartmentalized. And we're creating air barrier assemblies with air barrier materials to create whole systems. You see, air barriers aren't installed, they're created. They're created by you, by me as a manufacturer, and by the installers in the field to create that continuity. Because without continuity, the barrier doesn't work, whether it's an air barrier, vapor barrier, or water-resistant barrier. Continuity is important. Air permeance, all right? I mentioned that ASTM 2178. That's the mother's milk, the backbone of an air barrier material. You want a high-performance air barrier material, go with low air permeance, right? Not vapor permeance, air permeance. Remember, there's a difference. What about durability? You know, if an air barrier fails to be durable, that's going to be a problem. So whether it's a fluid applied or a sheet material or an SA or whatever, we want it to be durable because it's going to be buried in our wall assemblies. If it's not durable, we may have a problem there. Strength. What do we mean by strength and stiffness? They're kind of interrelated. Well, the mandate by the Massachusetts Energy Code, if you're doing any design work in Massachusetts, and by far, Massachusetts Energy Code takes the IECC, the International Energy Conservation Code, to the next level. And Massachusetts is the birthplace of the ABAA. It's the birthplace of air barriers in the continental U.S., below the border. Strength and stiffness are referenced in the Massachusetts Energy Code. What we want to do is that air barrier material needs to transfer the loads exerted upon it to the structure itself. If we're not doing that, guess what? We've got a weak point. So if there's billowing of the material, that creates a potential problem, all right? Then we'll look at a couple of these. So continuity, where does that come into play? Well, wall to foundation, wall to roof connections, wall to fenestration, right? We have to think of continuity. We build a wall. This right here is well on its way to being an air barrier assembly, right? Except for one thing, the continuity thing. What is the continuity of a 4x8 sheet of sheathing? Right, that lunch is kicking in all those carbs, right? 4 times 8 is 32. 32 square feet is your continuity of this air barrier material, right? And then we have to create the air barrier assembly. So the continuity with these sheathing materials are limited to the size, all right? And then we have an air penetration point. So we reference air barrier materials, they're air permeant, and using air barrier materials that have an air permeance of less than 0.004 CFM at a pressure differential of 75 Pascal, we can create air barrier assemblies, as I said before. Got a little bit ahead of myself. Sometimes I do that. We'll skip that slide. So here's an example of a barrier material, right, that may not be durable, right? How many times have we seen this, right? The wind got behind it, started blowing things off. So that becomes suspect. Durability is important. Remember this, right? Buildings, they suck and they blow. They do both. Rarely, if ever, are they perfectly balanced. And an air barrier resists air flow in both directions, all right? If your building is conditioned using, a lot of money to condition that air, right, and it's leaking that air to the outside environment, guess what? The thermostat kicks in, right? Whether it's cooling or heating, and the owners are spending more money, right? Owners don't spend money when their thermostat isn't running, when their HVAC system isn't running, right? But they may be costing themselves if air leakage is occurring and bringing in moist air, right? So this is whether the HVAC system's on or not air barriers are still delivering value to the owners, all right, by protecting this, the building. So this is the good stuff, the codes, right? And this will be interesting. So so here are some relevant abbreviations: the IECC, the International Energy Conservation Code; the IBC, the International Building Code. If you're doing residential work, which you might be doing multifamily but not single family. Single family would be IRC. 4 units or more come under IBC. Air Barrier Association of America. All right, that's an important organization that is really elevating the status of air barriers and education and whatnot. They qualify contractors. They have a quality assurance program, and then we have the ICCES. Anybody hear of the ICCES? International Code Council Evaluation Services. Thank you. Yeah, we're going to talk about that because that's important. I was listening to a manufacturer give their AIA program on air barriers, and he made the statement that there is no standard for water-resistive barriers. Patently false. Another manufacturer I saw on their website, of all places, that they said that they are the only air barrier that is NFPA 285 compliant. Again, patently false. Unfortunately, sometimes the marketing departments run ahead of the technical departments and put out information that is misleading to the public, and that's why I get a phone call like I did last night at 6:30 saying we have to redesign the building because it doesn't meet NFPA 285. And that may not necessarily be the case. They were just led to believe that it does. The energy code is where we find air barriers addressed. The building code is where we find vapor and water resistive barriers. So if there is any indication that the two are not the same, air barriers and water resistive barriers, it should be apparent to us in the fact that they're in different codes, right? But if that still doesn't convince you, let's look a little bit further. Air barriers are defined technically. There's a technical specification for an air barrier, and if you're writing a specification for a project, you want this in your spec. Bare minimum, you need to say that the air barrier materials shall have an air permeance of less than 0.004 CFM. Here's a guy down in Florida, Dave Smith, good friend of mine. He's creating an air barrier assembly. Look at that, right? Remember I said about that continuity? He's joining the air barrier material here with the air barrier material here that's separated by a joint by using what? Another air barrier material. We use air barrier materials to create air barrier assemblies. When Dave's done here, he'll tie into the roof air barrier, into the foundation, and guess what? Voila, we have an air barrier system. But we don't do that. Imagine how much money we could save if we did what this innovator, Dave Smith, is doing. Well, reality is that while that meets the energy code, it doesn't meet the building code. Now, what does the ABAA have to do with everything? Well, remember that definition of an air barrier in the energy code? It says air permeance of less than 0.004 CFM at a pressure differential, that air permeance. ABAA said, you know what? There's more to air barriers than just its air permeance and installing them continuously. That's not enough to safeguard the building. And so the ABAA said, besides that air permeance that is required in the energy code, we should also look at, voila, water resistance per AATCC 127, right? The hydrostatic head test, right? Then what about nail sealability? If we're putting this on the outside of our sheathing, does a build, unless you're building in West Virginia, no offense to anybody from West Virginia, but I always drive through West Virginia. I'm like, when are they going to finish that building? You see houses that have been wrapped in Tyvek for 6 years, it looks like. But the nail sealability, right? Claddings have to be installed through that, right? So nail sealability matters. Pull adhesion, crack bridging are related to fluid applied barriers. But interestingly enough, and this escapes some people, the Air Barrier Association of America, guess what? Qualifies air barriers. They do not qualify water-resistive barriers. So even if you go and get a higher performing ABAA qualified air barrier, that doesn't guarantee you that you have a water-resistive barrier, because they're not testing for water. They're just doing an incidental one test, the ATCC 127 hydrostatic head test. This is what the building code, all right, we're changing from energy code to building code. This is what the building code says about a water-resistant barrier. 1 layer of 15-pound felt. Remember this? When I worked with DuPont, this was our biggest competitor in the marketplace, 15-pound felt. We don't see it that much anymore. Architects, builders, they all moved to something else. Why? Because it wasn't that durable, all right? It had much lower vapor permeance than tie-dye. So we saw the technical benefits of moving to a spun-bonded polyolefin versus, felt that was, impregnated with asphalt. Nevertheless, 15-pound felt is specifically called for in the code. And I bet it's been 5 years since you guys had felt on one of your projects here. It's been longer. I was being nice. I just covered my bases there. Yeah, it's been longer, right? Well, guys, if you're not using felt, you're not following the code. This could be a problem, right? Because the code is oftentimes referred as the minimum. And if you're not using this black asphalt impregnated felt, you want to make sure that what you are using at least meets this requirement. And we do that through an acceptance criteria. Now, I want to point something else. It says other approved materials, right? Section 1404.2 says felt or other approved materials. Now, who is the approving body? Who approves that? You guys? No, right? Your engineering firm? No, not them either, right? Other approved materials shall be attached to the studs and sheathing. Remember how I said air barrier, you can put it anywhere you want, designer's choice? Not so with a water-resistant barrier, right? Water-resistant barrier is specifically called for over the face of the sheathing or studs in open stud construction, which we don't see too much of anymore. And you know what? Here's an ICC code report. This one is for Georgia Pacific Dens glass. And when I open it, I see that when installed on exterior walls and soffits, the sheathing must be covered with, and I quote, an approved water-resistant barrier. Not an air barrier, right? If I go to James Hardy's technical their code report, I read under conditions of use that the siding must be installed over, and I quote, a code complying water-resistant barrier. This is important. It doesn't say an air barrier because it doesn't matter to James Hardy or to Georgia Pacific. If air touches Dens glass or wood-based sheathing products, it touches it, right? But if water does, that changes the whole dynamic, right? And the warranties of these manufacturers, they're tied to this as well. It says if there's any confusion or any conflict between anything that you've heard, read, or seen, right, this prevails. So if the manufacturer says, yeah, you're good there, just use us, right? That doesn't resolve you. Ignorance is not an excuse for following what actually becomes incorporated into the law. So very important there because air barriers are not the same as water-resistant barriers. Now, flexible flashing, we mentioned before that we use flashing as a water management tool. Well, guess what? There's an acceptance criteria for both water-resistant coatings used as water-resistant barriers and for flexible flashing materials. Include them in your specification to safeguard you, to ensure that the materials being installed meet a minimum of the code and probably go well beyond the testing that has been done by any of the other air barrier manufacturers. How do you know if a fluid applied air barrier also is a water resistant barrier? Well, they should have a code report, right? An ICC ESR. So this is all the testing done and incorporated into AC 212, the acceptance criteria for a water resistant coating to be used as a water resistant barrier. You can see there's quite a number of tests. Let's look at, well, the difference between what ABAA does. ABAA does this one, and this one, 1970, the nail sealability test. ABAA uses 2 water tests, all right, in their qualification of air barriers. That is in stark difference to what the ICC and their acceptance criteria require for testing of water-resistant barriers. Right? Here's a typical standard test, ASTM D1970, nail sealability test. Get a paint can, punch out the bottom of it, put 2 smooth shank roofing nails through it into a sample of material, add a hydro head, drop some dye in it, wait 72 hours, see if it leaks through. Voila, if it leaks, you got a failure. If it passes, you pass. Everybody passes this test. Now let me ask you, smooth shank roofing nails, steel stud construction, do we do that? Right? It's a weak test at best. All right? Higher standards are required, and some manufacturers, including some that I'm intimately familiar with, have implemented much more rigorous testing. This is ASTM E331 that's been modified. E331 is the fenestration test, right? The dreaded spray test. You get the spray rig up there on the 7th story and spray a window for 45 minutes and see if it leaks, right? What else is going on? On the inside, you got a giant fan working in reverse to try to suck the water through. So you're spraying on one side, you're sucking on the other, you're trying to pull water through. And what changed here was we didn't put a window in. We put fasteners. And over 45 minutes and 210 gallons of water sprayed on this in this third-party evaluation of this material, they found not one leak, right? They used materials that were 9 times thicker than this material, and it leaked at the first pressure differential. At its highest pressure differential, it replicates a Hurricane 3 category wind-driven rain, right? And there's a material, talk about material science, that is ABAA qualified as an air bearer, doesn't have ICC AC212 approval as a water-resistant bearer, but is still being used on frame construction, and voila, at the lowest pressure differential, within the first 15 minutes, it was leaking like a sieve. All right, air barriers are different than water-resistant barriers. Water-resistant barriers go through much more stringent testing for water resistance, and they're full assembly. All right. So what does AC212 include? Structural racking, restrained environmental, hydrostatic pressure, freeze-thaw. Look, what happens to roads in Pennsylvania? I grew up in Pennsylvania. Water gets into the cracks of the concrete, expansion, contraction, it busts up concrete. What do you think can happen if a water-resistant barrier, which is intended to get wet, right, goes through freeze-thaw? ABAA doesn't test for that, but the AC212 incorporates that. Very important. Among a long list of other things. And voila, once you meet AC212, you can always do the air permeance test. That's easy. I mean, heck, guys, we already determined that just drywall itself has an air permeance of less than 0.004 CFM at a pressure differential of 75 Pascal and meets the energy code as an air bearer material, right? The more stringent test is AC212. And it's what gets us into trouble. When buildings leak water, that's when the phone calls start. Fire propagation. I mentioned that, there's a lot of confusion still to this day, but I think we're getting past it and we recognize that NFPA 285 is an assembly test, right? NFPA 285 is supposed to stop this from happening, and that is namely vertical fire propagation, right? It's a big problem because guess what? With the introduction and the adoption of the energy code, we seem to be doing this, taking foam insulation and putting it on our walls. Why? Because in 98% of the cases, we meet the continuous thermal envelope requirements by doing this, continuous insulation, right? The problem with this, regardless of the color of the material, is it burns, all right? And it results in things like this, all right? Everyone probably remembers last year that the fire in England, right? That was vertical fire propagation, right? So what do we got to know about this? Well, I have a brochure here that you can take with you that kind of talks about NFPA 285. Now, the good news is that NFPA 285 applies for types 1 through 4 construction. If you're doing type 5 construction, it doesn't apply. So a multi-family type 5 project would not necessarily require NFPA 285. And NFPA 285 is also based on the height of the building, 40 feet. 40 feet or more, NFPA 285 is triggered, okay? Why is 40 feet important? Why 40 feet? Why not 20? Anybody? No? fire equipment. The ladders can't get up there, right? After that, it's the building's toast, right? So that's why this is important, because modern firefighting can only go so far. And once you're above 40 feet, and many buildings are, right, that's only 4 stories, 3 stories, NFPA 285 kicks in. The use of continuous insulation is also a trigger point for NFPA 285. Now, think about this, type 3A construction. It's residential, but it's not type 5. Does NFPA 285 apply? Yeah, it does, right? We have commercial walls and residential type walls that are coming together. They're often type 3A is often over 40 feet, boom, NFPA 285. And we can work through this. You know, manufacturers can work through this and give you something that meets NFPA 285. But the reality is, it's assembly specific. If I gave everybody a napkin and said, your architects, draw me a wall, how can I come out and say, yeah, I meet NFPA 285 in every instance? I don't know what you've built. It's an assembly specific test. We've got it, as a manufacturer, we've got to sit down with you and say, yeah, we've got testing to demonstrate NFPA 285 compliance. Reach out to your manufacturer and ask for it in writing. Don't take their word for it, because, you know, some of these guys are, yeah, we meet that. When they can't say that. It's just, you can't do that. All right, so really summing things up, you know, air control is the function of an air barrier. Water control is the function of a water-resistive barrier. Air barriers and water-resistive barriers are different. Air barriers stop and have been tested and proven to stop or retard air. Water-resistive barriers have gone through much more stringent testing under AC 212 to demonstrate compliance with Section 1404.2 of the IBC, as well as functioning as the code requires a water-resistive barrier. There is the possibility to get a material that is both an air barrier, ABAA qualified and IECC compliant air barrier, and also a water-resistive barrier, but ask for the code report to prove that. Because many air barrier manufacturers would tell you that, well, yeah, we're an air and moisture barrier. The code makes no reference to moisture barriers. What is a moisture barrier? I don't know. Do you? Right? What is the technical definition of a moisture barrier? Right? An air barrier may stop moisture-laden air, but is that a moisture barrier? So we know what the definition of an air barrier is. It's defined in the energy code, ASTM 2178, an air permeance of less than 0.004. We know what the definition of a water-resistive barrier is. It's defined by the test set contained in AC 212, the acceptance criteria for water-resistive coatings to be used as water-resistive barriers if you're talking about fluid applied. If you're talking about sheet membranes, it's AC 38, acceptance criteria 38. Advances in material science have done a lot to improve the performance of our barrier systems and, interestingly, reduce our VOCs, reduce our owner's costs and installed costs, while at the same time driving huge performance gains. All right, thank you very much. And I apologize for speaking so quickly. But any questions from the group?
Question.
Please.
So, of course, I know that they're different, so the answer is to find one that does both.
Well, you're in luck, because before you stands a manufacturer that has a material that has passed rigorous examination by third-party evaluation, the AC 212. So BASF has a fluid-applied air and water-resistant barrier. So we're an ABAA qualified air barrier. We go beyond the energy code and perform at the level of but we also meet AC 212. In that one slide that I showed with E331 testing, the 45-minute water test with all those fasteners through it, that was our material actually being tested. You can kind of see because it's gray, and this is our system.
On a perfect world, we just lacquer all 6 sides of the building, and then we're good to go.
Well, as long as you have continuity, right? I mean, because continuity required, no matter how good an air barrier you have or a water-resistant barrier you have, if you don't have continuity, you're going to have trouble, right? So we have to pay attention, and a big part of it is our roof tie-ins, our wall-to-foundation tie-ins, also our flashings. Pay attention to your flashings, because you think that air barrier should be continuous. unless the flashing material itself is an air-bearing material, in which case you could tie in at the top and tie in at the bottom, right, to connect. So the attention to the details is what guarantees our continuity. Also, high roof, low roof, right? We'll come up on one side of the roof, and then we'll terminate at the top, and we won't come down to tie into the air bearer material of the higher or the lower roof, right? So we want to make sure that we have, so all continuous 6 sides. Take your pen, start tracing that air bearer all across, and that, so, yes, please.
Can the AIA sign in for me?
Oh, I'm very sorry. I meant to pass these off. I have several, and we'll consolidate it, so. I'll take you around.